I don't have a binary TPM myself, but you have, so it's a style that it can be done. So we can look at the eclipses, and when we have you give me the temperature field, and we can have it. We can have this field to go through the thermomechanical model and predict the crack growth. That's the idea.
Okay, thanks. Let's move on. Next talk is Jürgen Blum, thermophysical modeling of granular surfaces.
That's fine. Yeah. Thanks. I took the liberty to change my title. It didn't make it to the program, however, so you'll see what we'll be talking about. So I changed the title because I want to study how the regular forms, changes over time, and is observed today. So this is I think the part of the complete regolith story. We have regolith formation, and we've just been talking about it in the last talks, but impacts, impact gardening, and after the impact, part of the regolith produced little fast particles may the cell body being impacted. The rest falls back, which can lead to size sorting. The deposition is interesting. That leads to some stratification. I will be talking very briefly about that. And so this happens over millions and billions of years. And in between, regolith may change by thermal fatigue, as we've just heard, or by flow avalanches, Brazil nut effect, and so that we end up at the regolith which is observed. And we've heard in the last couple of days a lot of information about that, how to absorb solar radiation. Is it by surface or in the volume, in a subsurface volume? Which wavelengths penetrates? How deep? What is the influence of the physical parameters like albedo, solar elevation angle, granularity, shadowing, beaming parameter, whatever, you name them. And then the volume or the surface of the regolith re-emits infrared radiation, and all is determined by the heat conductivity and radiative energy transfer into the interior and out again. And this is modeled. We end up with a temperature stratification, as we've just seen, and then the model ends up at an infrared flux at different wavelengths, and we infer the regolith from that. So that's the story, I think, and I want to pick up some points here to hopefully add some information for you. This is a study we're working at, how regolith forms. So we start with a 100-kilometer radius object with an initial volume filling factor of 6%. That's the red color here, so 40% porosity. That's the dense packing of the material it formed out of. This is 100% of the surface, so take like 10,000 elements, do a statistical analysis. Initially, it's the dashed line here, so it's a spherical body. And then we let it evolve by impacts from meteorites of all sizes between 10 centimeters and a catastrophic impact. And after 4.5 million years, we have a sorted surface elevation level here. We have 10 kilometers of regolith formed at some points, and we have a depression of whatever, 20, 30, 40 kilometers at other points. And we see those with the depressions are the highly compacted material, and those with the with most of the regolith are still like this. So we're interested in the top meters here of regolith, or centimeters even. And that is what I will be talking next about it. However, to understand that, and this is in the laboratory session, I remind you, we did some experiment how regolith is stratified when it forms. So we did a parabolic flight. This is a 0G flight, so this is G level. You see this goes down to 0 now. So this is as good as it gets in a parabolic aircraft. And we added 5% per G by accelerating the experiment upwards, and measured in 4 tubes with the same type of material at different grain sizes, the height of position, and at each time we know the G level. And you see it's difficult. After the parabola is over, we return to the 1.5 or so level afterwards. Sometimes you get lunar parabola also. So you see still at the acceleration level at some point, I hardly can see it from here. You see the deposition velocity is very, very high. And at some point, we turn into a lunar parabola, and then the deposition velocity gets lower. Well, another shake maybe. This is real time data, so I have to be patient. Okay, now we're in the lunar parabola, and we should the fill heights at different D levels, lunar, Martian, and about 5% plus minus whatever the plane gave us. And here is the results that has just been published a couple weeks ago in Icarus, the forthcoming issue actually. So this is for 10 micron grains, 60 micron millimeter, and agglomerates of micron-sized grains, and we models of stratification of regolith to the data. You see the fit is not excellent, but we somehow find envelopes here, which with which we worked in that particular paper. And one of the results of the paper is this plot here on this side. This is the height of the regolith. So a meter is like here, a millimeter is here, or a variety of bodies for which we previous work, we'll be talking about that in just a minute. We determined the average grain size. So for Dodona, it's 0.6 millimeters, Phobos 2 millimeters, Steins, the Moon, 100 microns or so, Mercury, Vesta, and FG3. And you see the stratification. This is the volume filling factor. It all starts at 15, which is a random ballistic deposition. So this is 55% porosity level here, and this is the densest packing, random close packing. And you see typically the random close packing is reached at a meter level only. And if we take the lunar curve, which is number 4 here, so it's second in this plot, and we take a centimeter depth, at a centimeter we haven't just reached the final packing. And it's nicely to what Paul told us this morning. So I think we have a pretty good agreement. The right plot is actually the same, but the sorting is different. The x-axis has changed from SI units to numbers of layers. So to better constrain sort the different grain sizes. You also need several layers, several 10 to 100, so thousands of layers of grain sizes before you end up at the closest packing. So I think it is really important for future studies of regolith thermal modeling to take into account that we expect a lot of stratification here. So this is the fairy castle's very low packing fraction, a very high porosity at the upper end of the regolith height, and the dense packing at the lower. But this is to hundreds of thousands of layers in between, and this is something to bear in mind for future studies probably. Okay, so the main part of my talk is our thermophysical regolith model. This is our strategy. We take what most of you guys are doing, namely observations, to infer thermal inertia and give us pictures of the observations. We take the material property of a particular object, derive the density and the heat capacity by the material properties of the object, assume a filling factor, just going back. Filling factor may vary a lot. Assume a certain fixed constant filling factor. Derive a model that I will be talking about in just a minute, and compare it with that filling factor to the heat conductivity, the thermal inertia observed by some of you, will give us, if we have a match for the same material, the same porosity, we can derive a grain size. And that is the main output of our study. We derive the typical grain size, which is not the typical grain, the optical properties, or not thermal properties, but is the typical, the thermal, yes, it's a typical grain size for the thermal properties, not necessarily for the optical. Okay, of course, we do have a lot of simplifications. The volume filling factor, as I said, is assumed to be variable, but not within one calculation. So it's constant for each calculation. So we don't take stratification into account. We only use albedo, no beaming parameters, something like that. Albedo even, if we use albedo, only one temperature, namely the one given in the studies, on one particle size, no size distribution. We'll see why in a minute. And we only the stationary solution. The physics we apply that, we have a heat conductivity model through the network of grains, and that model is good for only one particle size, as you will see. And also take into account radiative heat transfer. We assume an specific unity, but 0.9 or so would also do the job. The results would be very, very similar. We have a free path model here, and we calibrate everything on lunar regolith. I'll show you that in a few minutes. Okay, this is in principle works. The heat is transported through a network of grains through the very little microscopic contacts, or it's transported through the pores between the grains. We can also add gas if we want to apply that model for comets, which we actually developed it for. So this is, we're allowed to show formula. I learned in the last few days. So this is the heat conductivity through a network of grains as a function of size, as a function of temperature in every layer, as a function of porosity, which is variable but a constant in each of the simulations. It has two terms, namely the network conductivity and the radiative conductivity. This assumes an emissivity here, which we assume to be unity, a temperature, and a mean free path. And this assumes a Hertz factor. And fortunately, we dug out literature, a paper from 1973 by Cont and Tien, by the name of conductance of packed sphere and vacuum. So they derived the heat conductivity, the Hertz factor, actually the Hertz factor for a network of grains under external load. So the only thing we did to the model, we replaced the external load to the internal load, which is the interpart forces. Small grains exert interpart forces onto one another, and which is what you're seeing here. So this has elastic properties, the Poisson ratio, elastic modulo, and the surface energy of the material, and these are all temperature dependent, and the grain size. And so the geometry, actually the packing fraction, or the phi expression only enters here, and we took the liberty to take the 3 data point from the BCC, FCC, and SC lattices that Chan and Tien had used, and apply some crude formula here. You see it doesn't fit extremely well, but within 10 or 20% or so, we're fine with that. And we use that to extrapolate that to lower velocities. So this is this factor with these constants. I'll be talking about the only fudge factor we're having in the model a little later when we're going to irregular grains. For the moment, this is unity. And the conductivity by radiation, we take the mean free path. This is this formula, and we use the data from Skoro et al. That's theoretical data, and fitted a typical function for that kind of work to the theoretical data with the only fit function, the E1 here. In the end, we end up at this with a unity no fudge factor, actually. So this is the nice thing of that model is it doesn't have a free parameter to play with. This is like models that predict without the liberty of changing parameters here and there. So actually, every parameter should be known. If we're doing with spherical grains, the rate is known, the material property should be known. That's another material property. The filling factor known, constants known to some accuracy. So this is nothing to excuse yourself if it doesn't fit. Okay, this is the laboratory section. So we did experiment. Shown an artificial light, sunlight onto a cylindrical sample, measured by a camera the surface temperature, kept the bottom temperature constant, took different grain size, actually spheres which were pretty monodisperse, and took different heights of the sample. Here are our 6 samples, very fine grains, all black spheres, and to the large grains, so between a few 10 microns to about 1 millimeter or so in grain size. Black spheres with a very narrow size distribution. The actual size distribution is given in the paper. we treat them as monodisperse. Okay, here's a typical plot. Over time, sun on, temperature increases, reaches saturation, and this is what we're measuring, temperature difference between the top and bottom, and this is all we need for the stationary solution. Okay, here's one of the validation plots. So this is for 1 grain size, the temperature of the surface as a function, well, the temperature change because the height of the samples changed, illumination intensity changed, and here's the data. Data is extremely noisy. Data, unfortunately, is always very noisy, but the predicted formula, including radiations, the filling factor of the samples between this and that line curve. So this is pretty good. A form without radiative transfer and a constant surface energy doesn't fit well, and the other mean free paths also don't fit well. So I think this is an acceptable validation. We did another one. We changed the grain size. So in this study here, this was the grain size. We had it done in an earlier study with micrograins, and here this is the data. And the model functions are again between this and that line, and you see they fit the data without being fit. So no free parameter here. So I think this is a very good agreement, so that we can believe that the model predicts something that is sensible. So this is the complete model, except for the case that what we referred earlier. We've seen pictures. The regulus is irregular, so not monodisperse. But about the non-monodispersity we haven't yet. But the non-irregularity we hit in factor here. So this or whatever it is in English. So this fudge factor should deviate from unity. And to derive that or approximate that, we used data from the moon. So we used lunar regolith data published in the literature, grain sizes, so the surface energy and the moduli and everything else. So you can read it here. And took data taken measured in the 70s of the heat conductivity, lunar regolith as a function of temperature. This is the laboratory data from the 70s, the data points, the X's and the pluses, 2 papers, and model now with the only factor is the dashed curve here. And it turns out that this fudge factor is about 0.5, or very close to 0.5. So without radiation, the model, and without radiation, the model would predict that. Only radiative transfer, this is this, and the sum of both very nicely shows you that radiative heat transfer at these temperatures, which are very relevant for the lunar surface, is an important factor. So we assume that fudge factor 0.4 plus minus a little, so which is close to unity, and it is smaller than unity, which is what was earlier, that regular grains should have smaller contact areas than regular grains. So we're pretty sure that we're not too far off with that model. And again, a comparison to the moon. So this is the model scales with the size of the grains. For small grains with inverse to the radius to the power of 1/3, so r to the power of -1/3. For small grains, large grains, the mean free path formula comes in, which has a linear relation to r. You see that here for small grains, you have a -1/3 power. Large grains have a positive d of power. So our typical curve looks like that for a given filling factor or porosity. And then we fit these curves, or we match these curves with the predicted heat conductivities of, and that is the lunar regolith. Actually, the gamma value, thermal inertia, given in the papers from the 70s was 48 in a unit. We couldn't match 48, as I'll show you on the next plot, but with 60 we could find a very nice match. So 48 is 60 instead of 48 might be fine. So the X is where our model fits the heat conductivity measured independently, and that gives us a grain size. Okay. However, as I showed in the beginning, we do have the liberty of playing a little with the volume filling factor. So this is the heat conductivity now taken from a thermal inertia of 48 SI units, which gives us a heat conductivity like this, or 0.1 filling factor, 0.2, 3, 4, 5, 6. And here you see why we couldn't find a match filling factor of 50% was the previous plot, because our curves vary with a factor like this, 0.1, 2, 3, 4, 5, 6, and we don't get a joint value here, only for the lowest filling factors, 0.1, 0.2, and 0.3. So this indicates that the volume filling factor of the lunar regolith at the depth we're looking here for in the measurements is pretty low. However, the size dependence on this effect is very, very little at the low filling factor. They would be larger at the high ones, but we don't match. We get a pretty good agreement. Now we applied this, this model to asteroids. You need more material parameters. So of course, always a tricky business to get the material parameters right, the right type of asteroid, the temperature dependence of the material parameters. It is always a tricky business. However, I show you one of the examples. That's Itokawa. Again, these are our 6 curves from our model, again with filling factor 0.1 through 0.6 here. And this is these are the 6 heat conductivities derived from a thermal inertia of 750 SI units. And your matches are here, which give us a spread in sizes of a centimeter or so of regolith grain, which is pretty agreeable to what was directly observed. So we did this for a variety of data that was measured by many of you, and we've seen on the first day a few times Marco Delbo's plot on thermal inertia versus size of the parent body. We converted that into grain size as a function of gravitational acceleration, the 3 types of SC and M class body, and we could find a very nice correlation here. The higher the gravitational acceleration, i.e. the bigger the body, the smaller the regolith is on average. But there's a lot of scatter here, but the small bodies typically have the large regolith grains, whereas the large bodies have the small grains. And one can, of course, readily explain without model it as a function of, this is gravitational acceleration, so escape speed also scales with that value. The higher the escape speed, the easier it is for the body to recapture the complete set of formed regolith particles, which is very hard for the small bodies to do. They only recapture slower particles, which on average are the larger particles. So this is the explanation without having modeled. Finally, the paper by Enrosidis, I think all the co-authors and authors are in this room here, published last year in Nature, of the asteroid 950 DA is a very nice example to also test our model. They found a distribution of our probability distribution of thermal inertia between 0 and 75 or so in SI units, and they found that about half of the surface of the asteroid had a negative gravity. So the rotation was so strong that the gravity, residual or actual gravity, was showing outward, which leads to a negative G level here, which requires, in order for the asteroid to survive, in a certain cohesive strength. And that's another thing we can derive from a grain size, and that is what I like to show you. So this case of 1950 DA, thermal inertia, thermal inertia between 0 and 75 is allowed. So we tested 4 types of classes, M, E, N side, S, and D, with a given certain porosity now, 50%. We found an agreement here, but not with the range of thermal inertia given. The range of thermal inertia given, only the 2 are allowed. So we're talking about grains on the order of 100 microns. And as a function, and now for only S class, as a function of the porosity again, so filling factor, sorry, I forgot to write down which is which, but it doesn't matter. You have seen it before. So different filling factors here. We good matches for all the 6 filling factors, and for all the in the range of the thermal inertia given. However, now the strengths come into play. Which one is the right one? And we believe that we are close to the right one with a thermal inertia of about 40. Yep, that's done. With a radius of 62 micrometers and a which gives us then a tensile strength, a cohesive strength of about 45 Pascal, which is here. So going back this is this curve, so this is the size. If went down to another filling factor, this would give us a factor of 2 smaller grains, so about 30 microns, which as the strength increase inversely linear to the size, would give us 90 pascals, which is out of the range given by Rosides et al. In the paper. So we can constrain this pretty much, and also the filling factor to about 50%, plus minus a little bit, and only a little bit. Okay, I need to talk about quaternary surfaces. I'll leave that out. So coming back to the regular story, I could show that formation and stratification is important to characterize when you're interested in regolith. Press A regolith, but the modeling requires some discussion, which is concluded here. Thank you very much.
Jürgen, where would 1950 DA be in your plot of grain size versus acceleration?
Oh, yeah, that's a good point. And can you remind me how big 1950 is? 4.3 kilometers. So
1.3.
1.3. So it's the gravitational acceleration is about here. Grain size was 60 microns, which is about here. So it would be here, down here. Which is exactly what we expect. If centrifugal force drives off everything that whose tensile strength is lower than the value required.
Yeah.
It will fly off, which will be the big grains. So it retains the small grains only.
It's a very weird object because it's the thermal inertia doesn't fit in the plot, and it's interesting. But yeah, maybe.
Maybe logical.
Agree with what you say, and I would add that when you have small objects with complicated shapes and complicated potential surfaces, in addition to removal of regoliths for any as a consequence of any mechanisms producing some shaking, but there will be also mobility of the regolith that will tend to occupy to settle down to the zones that are potentially was the gravitational potential is less. So this is also important.
I could not agree more. So this is this part. So what happens between the formation and the observation? Of course, you're right, and there's more than that.
So I really like your model a lot, being able to estimate the grain size from the thermal inertia. One of the questions that I get when I present like that to people is, what does that grain size represent in terms of the real distribution of grain sizes on the surface? And I never know what to say. So what's your answer to that question? Is it?
I don't know it either, Bert. Of course I don't know it, but let's go back to that plot where I showed it. The principle. Here you go. I think our grain size is more the average mass-weighted grain size. This is where the contacts are between. However, of course, you can think of nasty size distributions where a little grain always is in between a large grain. The little grain would determine the heat conductivity. In that nasty case, we would probe something in between the smallest and the largest. But if the size distribution is such that the bulk of the contacts are between those dominating really the volume, then I would think we're towards the upper end. And if we compare it to the lunar values, where we got it here, so our value is here. This is the vertical line, are the range of lunar regular grain sizes. So we're towards the upper end, which is also indicative of that argument. But I'm not sure about it. So nobody has really modeled it with nasty size distributions.
So the thermal inertias that are derived remotely are relative over the couple of skin depths down from the surface, right? And if the regolith grain bigger than that, then you're going to get a bare rock value. So does your model kind of account for that?
Just if there's a bare rock within the
grains comparable to the thermal skin depth having higher thermal inertia.
Yes, I think the validity of our model ends where the grain sizes are so large that diurnal skin doesn't heat them to a constant temperature. So there is a limit to it. I must admit, I haven't calculated, but much more than a centimeter, I wouldn't dare think here. And this is where the Itokawa had an SI gamma of 750. Bare rock has a gamma of, does anybody know by heart? Yeah, it's not much bigger. So this is where I think model ends. And the reason is, I think that grains this big, that they match the thermal inertia of bare rock and don't reach equilibrium temperature in a diurnal phase. So does it answer your question? Thanks.
You go back to the gravitational plot, this grain size. I was wondering how much a contribution, like the bigger asteroids are going to be older, and so they've had more time to produce finer grain regolith. How much is that contributing to that trend you see?
Good point. I think any asteroid above 100 kilometers or so is super old. The spread here for those that are big is very little, so they you can tell they were younger. Yeah, they could probably also show us something. I'm not quite sure whether the size dependence is affected by the age. I'm not sure about it. So that depends on things that happen in terms of size sorting over millions and millions of years, other than by impacts. Yeah, sure. They clearly are younger here. Their collision lifetime is short, but they change the size distribution. It only changes the depth of the regolith, but they are for a 100-kilometer object. That's about 10 kilometers. So that's, of course, for a younger object that's shallower, it's probably still deep enough to be not bare rock.
Okay, thanks everyone. Let's break for lunch.